In the last couple of videos, we learned how to calculate regression coefficients, standard error of estimate, and R-squared or goodness of fit. I would encourage you to watch those before watching this one. In this video, we will learn how we can use Python to perform regression analysis. Recall that the capital asset pricing model or CAPM describes the relationship between market risk and return for any security. We can loosely describe the CAPM equation as the return on stock I or YI equals to the risk-free rate or alpha plus the market risk factor or beta times the return on the market or XI. The beta coefficient tells us about the riskiness of a stock. Higher the beta, higher is the risk. In general, stocks with beta greater than 1 are the riskier or aggressive stocks, as for every 1% change in the market returns, the return on these stocks changes by more than 1%. Similarly, stocks with beta of less than 1 are known as the defensive or less risky stocks. For these stocks, the returns changes by less than 1% for every 1% change in the market returns. Let's say we want to calculate beta for the stock of Apple. We went through the process of manually calculating beta in one of our previous videos. Now let's see how Python simplifies our calculations. First, let's import our standard libraries. Now let's download a sample of daily prices from Yahoo Finance for Apple and S&P 500 index, which can be used as a proxy for market returns in our CAPM equation. Let's download the data for the past 5 years. Let's call the new dataset prices. Once we execute these lines of code, Python will pull the adjusted closing prices for Apple and S&P 500 index from Yahoo Finance. Now let's calculate the log returns by executing the following line of code. Finally, we can drop the missing observations by using drop_NA function. Recall, to calculate the beta coefficient, we will need the covariance between the returns on Apple and S&P index, and we will also need the variance for returns on S&P index. Using the COV function gives us the variance covariance matrix. However, we only need the covariance. To do that, we can use the ilog function as follows. We multiply by 250 to annualize our daily covariance. We can use the VAR function to calculate the variance of market return. Don't forget to analyze it by multiplying by 250. Finally, we can calculate the beta as the ratio of covariance and the variance of S&P 500 returns as follows. Now let's see how we can use the OLS function from the statsmodels.api to simplify the process. After importing the required library, we can define our y or dependent variable as the returns on Apple and our x variable as return on S&P 500 index. Then we run the following lines of codes to get the regression results. We can see that the beta value received from the output is the same as the one we calculated above. The beta coefficient of 1.1708 suggests that when the return on S&P 500 index goes up by 1%, the return on stock of Apple will go up by 1.1708%. Here is our coefficient of determination or R-squared, which tells us that about 55.3% of the variation in returns of Apple can be explained by the returns on S&P 500 index. This is our standard error of estimate and the t-statistic that tests if beta coefficient is different from 0. If we want to test if the beta coefficient is different from 1, we can do so by recalculating the t-statistics as follows. T with n-2 or 1483 degrees of freedom is equal to beta coefficient of 1.1708 minus the hypothesized value of 1 divided by the standard error of estimate of 0.027. This gives us a t-value of 6.33, which is greater than the critical value of 1.96 at 5% level of significance. Hence, we reject the null hypothesis in favor of alternative that the beta coefficient is different from 1.